Guys, so in this video we are going to talk about reactions of acyl chlorides. We've already done acyl chlorides in the previous videos. The first reaction that we have over here is hydrolysis of acyl chlorides. Hydrolysis is basically the reaction of acyl chlorides with water. So now in this reaction, water will act as a nucleophile. Nucleophile is any species that is uh, nucleus lover. Basically nucleus lover means that positive nucleus contains a positive charge, so this species is basically attracted to positive charge, attracted to positive or partial positive charge. Okay, now basically its proper definition is any species containing at least one lone pair. So basically another definition is any species with at least one lone pair which it can donate to the positively charged regions. Okay, now let's come to the main reaction. The overall reaction, the equation, overall equation is given over here. Acyl chloride, which is basically a 2-carbon acyl chloride reacting with water under no special conditions. Basically, this reaction takes place under RTP, forming the corresponding carboxylic acid from which it has been derived. The acyl chloride has been derived, and HCl is given as a byproduct because the acyl chloride will give out its chlorine atom, and it will combine with the hydrogen atom from water forming HCl, and then the OH of water will combine with the acyl chloride forming the carboxylic acid, and this HCl produced over here is in the form of white fumes, which are observed quite quickly because acyl chlorides, as we know, is very reactive, and we've covered the reason why it's reactive in the previous video. Now let's talk about the same 2-carbon alkyl halide with acyl chlorides. Again, we've talked about this in uh, quite detail in previous videos on alkyl halides. Basically, when the 2-carbon alkyl halide reacts with water, uh, this reaction takes place, the nucleophilic substitution reaction, and ethanol plus HCl are produced. But in this reaction, the conditions are harsher, they are stronger. So we have to heat it under pressure, and we have to heat it at approximately 100 degrees Celsius for about 14 days. Only then will this reaction be completed. So this again proves that alkyl halides are less reactive compared to acyl chlorides. Now let's look at another example. We have benzoyl chloride over here, basically the acyl chloride containing a benzene ring and a carbon double bonded oxygen with a chlorine atom attached. Okay, now in this case water is again used as a nucleophile. Water again will give its OH to the carbon atom, forming the corresponding carboxylic acid over here, and HCl is again given as a byproduct, and again no special conditions, RTP is used. So this basically means again that the acyl chloride is very reactive, whereas if we react uh, the water molecule with chlorobenzene, we've done this reaction in the video on chlorobenzene. No reaction occurs, and we've discussed the reason why it doesn't occur due to the extended delocalized pi system of the chlorobenzene, which shields basically the positively charged carbon atom, and we've discussed the reason in quite detail in the video on chlorobenzene, so that's why I'm not going in detail on this reaction. But as a comparison, if we look at the two reactions, again chlorobenzene is less reactive compared to the acyl chloride, which is corresponding acyl chloride with a benzene ring. Okay, now let's look at the mechanism. This is the mechanism of the first reaction that we did over here, the first overall equation which is written over here of a 2-carbon acyl chloride with water molecule. Now let's look at the detailed mechanism. Okay, now water being a nucleophile will donate its lone pair of electrons to the region of partial positively charged carbon atom. This carbon atom is partially positively charged because it is attached to two electronegative atoms, oxygen atom and chlorine atom, and both are more electronegative compared to carbon atom. So as a result, the carbon gets a partial positive charge, and the oxygen and chlorine atom get partial negative charges. The nucleophile will attack the partial positively charged carbon atom. Be careful while drawing this black curly arrow. Its tail must start from the lone pair and its head must end at the partial positively charged carbon atom over here. Okay, because the examiner's cut marks if the arrow head and tail are not positioned properly. And then since this is a fifth bond being formed with carbon atom, and carbon is tetravalent, so one of the bonds have to break. The carbon oxygen pi bond breaks and both the pi electrons are transferred to the more electronegative oxygen atom, forming this species as an intermediate. This is an unstable intermediate that is formed, and now this oxygen atom over here has a positive charge because while forming the dative bond it used both of its electrons, and after the dative bond is formed this bond acts as a normal covalent bond, so oxygen has lost one of its electrons. So oxygen gets a positive charge, and then this oxygen over here has gotten a negative charge because it has gained both the electrons of carbon atom. Now in order to achieve stability, this oxygen, to remove the negative charge, it donates its lone pair of electrons, forming a carbon oxygen double bond again. And in order to remove this positive charge over here on the oxygen atom, the oxygen hydrogen bond breaks through heterolytic fission, through heterolysis or heterolytic fission. This is basically this breakdown of bond is heterolytic fission or heterolysis. Uh, Through heterolytic fission, this bond breaks, and both the oxygen and hydrogen electrons in this covalent bond are transferred to the oxygen atom, removing the positive charge from the oxygen. And since both the electrons over here are also transferred in forming the carbon-oxygen bond, uh, the negative charge is also removed from this oxygen atom. As a result, we get our carboxylic acid back. And now over here, since this bond is breaking, the hydrogen over here is removed, forming an H positive ion. And at the same time, since now again the fifth bond is being made, again the weakest bond which is available in between the three will break. And since this is a polar bond, it will break. It is weaker and it will break. And again, heterolysis occurs and the carbon chlorine bond breaks and both the electrons are transferred to the more electronegative chlorine atom. H positive ion is released from the oxygen hydrogen bond breakage, and chloride ion is released, Cl negative is released from the carbon chlorine bond breaking. As a result, this H positive combines with the Cl negative, forming HCl molecule over here as a byproduct. And the molecule that is left is our carboxylic acid over here. Okay, so this was the detailed mechanism with water. Now let's talk about the reaction with NaOH. NaOH also provides its nucleophile by ionization in water. As NaOH ionizes, it provides OH negative, the nucleophile. Okay, now the OH negative will attack the acyl chloride again. The carbon partial positively charged carbon atom will be attacked, and since carbon is tetravalent, this time the carbon chlorine bond breaks directly and chloride ion is removed and the carboxylic acid is formed. The 2-carbon carboxylic acid, the ethanoic acid is formed. This chloride combines with the sodium ion over here from sodium hydroxide ionization, forming sodium chloride. And this ethanoic acid that is formed, it combines or reacts with excess sodium hydroxide because sodium hydroxide is a base and ethanoic acid is an acid. So acid-base neutralization reaction occurs, forming sodium ethanoate and water as a byproduct is given. And then again the overall equation is given over here. Ethanol chloride reacting with 2 moles of sodium hydroxide, forming sodium ethanoate, sodium chloride and water. And we've talked about the mechanism just now. Okay, and if the above reaction occurs, this reaction over here, it occurs rapidly at RTP. But if NaOH is reacted with alkyl halide, basically the alkyl halide given over here, The reaction will occur rapidly only on heating, again proving that this is less reactive compared to the acyl chloride. So heating is required again, and in the above reaction no heating was required, and the reaction occurred rapidly at RTP. So the reaction of the alkyl halide with NaOH under heat produces the ethanol and NaCl. This is basically a reaction from AS, and we've done its mechanism in AS, the SN2 mechanism. Okay, because this is a primary alkyl halide. Okay guys, so thank you so much. Meet you in the next video on more reactions of acyl chloride.